Have you ever stopped to think about how your computer is even possible? You've got a browser with 50 tabs open, you're playing a game, listening to music, all at once, and it just works. Well, the secret to that magic trick is a masterpiece of engineering called memory management. It's the true unsung hero of your digital life.
So that really is the central question here, isn't it? How on earth does your PC juggle all of that stuff at the same time with a pretty limited amount of physical memory? It honestly seems impossible, but it's a puzzle that computer scientists solved a long time ago with an incredibly clever, almost magical trick. All right, so here's how we're going to unpack this. We'll start with the core problem, what I call the memory squeeze. Then we'll look at the first simple solution and see why it crashed and burned, which introduces us to the villain of our story, fragmentation. After that, we meet the hero, a technique called paging, which sets the stage for the final act, the grand illusion of virtual memory.
Okay, first things first. Let's talk about the basic limitation we're up against, this memory squeeze. I mean, why can't we just stuff our computers with infinite memory and be done with it? Well, the best way to wrap your head around this is with an analogy. Just think of your computer's RAM as a small, exclusive parking garage right downtown, next to the main office building. That's your CPU. It's incredibly fast to get data in and out, but because it's sitting on prime real estate, it is super limited and super expensive. This whole concept is known as the memory hierarchy. It's kind of like a pyramid. At the very top, you have these tiny, blazing fast bits of memory right on the CPU chip. Then you have your main RAM, which is a bit bigger and a bit slower. And at the bottom, you have your massive but slow as molasses hard drive. You're constantly in this battle, trading speed for size and cost. And that trade-off is the entire reason memory management is so important. So, facing this puzzle, the early engineers did what any of us would do. They went with the most obvious, most straightforward solution they could think of. Just give each program its own single, dedicated parking spot. This approach is called contiguous allocation. The idea is simple. When a program needs to run, the operating system looks for one big, empty, continuous block of memory that's big enough and plunks the whole program down right there. It's easy, it's simple, but as it turns out, it has a fatal flaw. It really is a simple idea. But let's go back to our parking garage analogy. What happens when you have cars of all different sizes? Tiny smart cars, family sedans, massive pickup trucks, all coming and going at different times. You end up with a total mess, all these little empty spaces that are too small to be useful. And this problem, this plague of wasted space, is the villain of our story. It has a name, and that name is fragmentation. Now, there are two flavors of this villain. The first is called internal fragmentation. This is like when you need to park a tiny scooter, but the only spot available is one made for a giant truck. You take the spot, but all that extra space inside the parking lines, it's completely wasted. Nobody else can use it. But the real monster, the one that causes the biggest headaches, is external fragmentation. This happens when you add up all the little empty spots and you have plenty of free memory in total, but it's all chopped up into little useless pieces. You might have enough space for a bus, but it's spread out in 10 different scooter-sized spots. And this is the core of the problem. You might have 80 kilobytes of free memory, but if it's split into two 40K chunks, a new program that needs 60K is just out of luck. It can't run. Your memory turns into Swiss cheese. It's full of holes, but you can't actually fit anything substantial into it. For early computers, this was a showstopper. Now, to be fair, engineers tried to fight this. They came up with all these clever strategies: first fit, best fit, worst fit, basically different ways of trying to be smart about where they parked programs to minimize the gaps. But you know what? They were all just band-aids. They were managing the chaos, not solving the fundamental problem. A revolution was needed. And that brings us to the hero of our story, the paging solution. The idea is simple, but absolutely radical. It says, what if a program is like a big book? Instead of looking for one giant shelf that can hold the whole thing, why don't we just tear the book into individual pages, and then we can stick those pages wherever we find a little bit of empty space? This creates this incredible split reality. From the program's point of view, nothing has changed. It still thinks it lives in this perfect, clean, continuous block of memory. But the physical reality, it's been chopped into a million little pieces and scattered all over the place. This technique is called paging, and the most important thing to understand is that by allowing a program's memory to be non-contiguous, by not forcing it to be in one piece, it completely kills the problem of external fragmentation. It's just gone. Suddenly, every single byte of free memory is usable. So how does this magic work? It's actually pretty elegant.
You take the program's logical memory, the memory it thinks it has, and you chop it into fixed-size blocks called pages. Then, you take your actual physical RAM and chop it into blocks of the exact same size, called frames. And the secret sauce that holds it all together is a special map called a page table that just keeps track of which page is living in which frame. So here's the play-by-play of the magic trick. The CPU says, hey, I need the data at this logical address. Now that address is really just two things, a page number and an offset, which is just its location on that page. The system instantly looks up that page number in the page table map. The map tells it the corresponding frame number in the real RAM, and then it just combines that frame number with the offset to get the final, actual physical address. This translation happens billions of times a second. It's absolutely wild. But paging doesn't just solve fragmentation. It unlocks something even more powerful, a concept that I think of as the grand illusion, virtual memory. This is how your computer with 8 GB of RAM can act like it has 800.
Virtual memory basically takes paging and puts it on steroids. It's a technique that allows us to run programs that aren't even fully loaded into RAM. It creates this perfect, pristine illusion for every single program that it has a massive, private address space all to itself.
And the trick is just beautiful. We use our slow but enormous hard disk as a giant warehouse for all the program's pages. We only bring a page into that fast, expensive RAM, our downtown parking garage, at the very last second, right when it's actually needed. This idea is called demand paging. And how big is this illusion? Well, get this. A modern 64-bit processor can theoretically address 256 terabytes of memory. That's the space your program thinks it's playing in, even if you only have 8 or 16 gigs of actual RAM installed in your machine. I mean, this really shows you the scale of the whole thing. The logical space that a program sees is just colossal, while the physical RAM it actually uses at any given moment is just a tiny, tiny fraction of that. This is the magic that makes modern multitasking possible. This is everything. So in the end, memory management isn't really about organizing data. It's about creating a powerful, convincing illusion. The illusion of infinite, simple, private memory in a world of finite, complex, and shared hardware. And it kind of leaves you with a final thought, right? What other digital illusions are all around us, simplifying our lives every single day?